Hello. So now let us continue our lesson. Last time we introduced the Euclidean metric in 2 dimensions. I want this session. In this session, I want to introduce another metric for r squared, the plane, in 2 dimensions, and try to compare the differences between these two metrics, the Euclidean metric and the metric that I am going to describe today. The name of this metric is usually called the Taxicab Metric. Okay, but what is that metric? So let me have the coordinate system. As I told you that this is also a metric for the plane. So let me call this x-axis and this y-axis. Sorry, and then you have 2 points here, so let me call this point A, and I have another point B here. So here in this problem, my abstract set is just this plane, which is r squared, and the metric that I want to describe, I equip it with the subscript t for taxicab, and I would say that, okay, the taxicab distance between these 2 points is defined to be the absolute value of the difference between the x coordinates of these 2 points plus the absolute value of the difference between y coordinates of these 2 points. Okay, but of course still I need to show that this is indeed a metric. Okay, so if I say what is the domain of this, it is r squared Cartesian product r squared, but the output of course is a real number. So what is this really measuring? If you look at this, if you want to understand that, so if I go vertically down from here to here is x of a, and if I go vertically down here from here to here is actually x of b. So this distance that you can see here is just the absolute value of x of a minus x of b. So this one is a measure of how these 2 points of A are far away horizontally, and then for the same reason you realize this measures how far these 2 points are vertically. Yes? So this is the horizontal distance between these 2 points plus the vertical distance between these 2 points. For example, in this problem here, as you see, A has coordinates, so let me count them, 1, 2, 3, 4, 5, and then 1, 2, 3, 4. So it's 5 and 4, and B is equal to here 6, 7, 8, 9, 10, 11. So, and the y coordinate is just 2. So if I want to find the taxicab distance between these 2 points, I have to put 2 absolute values added. In the first absolute value, I write the difference between the x coordinates, and in the second one, I write the difference between the y coordinates. So the first one is 6, the other one is 2, so this is 8. So this means that the taxicab distance between these 2 points is 8. But of course, you can see that the Euclidean distance is not 8. Okay, so you can also calculate the Euclidean distance. So let me also do that for refreshing our memory. So let me equip my metric with E for Euclidean, and if I want to do this calculation, so if you remember, this is a square root of 5 minus 11 squared plus 4 minus 2 squared, and if I calculate that, it becomes square root of 36 plus 4, which is square root of 40, and I can write it as 2 square root of 10. Okay? Okay, so and then you see that of course this number is smaller than that number, so they don't coincide. Yes? So this is the really different distance. Okay. So in other words, what is this measuring? You can say that, okay, if I want to start from A and go to B, assume that you can always take horizontal or vertical steps. You are not allowed to go diagonally. Okay? And then this tells you that the shortest distance. For example, let me start from here. And for example, I can go here 2 steps, 3 steps, then I decide to go down, and then I go 3 more steps, and I go 1 down. So you see, so how many steps I take? 3 horizontal here, and then again 3 horizontal, so it becomes 6, and this is 6 actually. And then I take 2 vertical steps, and that is 2 here. So I have to take in total 8 steps to reach here. Okay, of course I can reach to B with more steps, but this is the shortest way I can do it. Okay, but let me say this is different from Euclidean distance, because in Euclidean distance the shortest distance between them is always one single path. There is only one single path that can take you from A to B, and that is the shortest one. But here, for example, let me change my color. I can do it like this. I can come here and then 2 steps down, and then finally go all the way horizontally. Again, if I ask you what is the length of this red path, then you say that 1, 2 steps again, 1, 2, 3, 4, 5, 6 steps. So again, in total, I am just following 8 steps. So there is no difference between the length of this path and the length of this path if my meter is actually the taxicab metric. Okay? And then if I want to go from A to B, this is the optimal way I can do. I have to take the lowest possible steps that I can take to go from A to B if I want to respect the rules of the game, meaning that I have to go either horizontally in each step or vertically. Then this is the minimum possible number of steps that I can take. Of course, I can go with more distance steps. So I can, for example, start going up. I am going vertically, then I can go horizontally, then vertically, then horizontally, then I can go up vertically, go here, and then come back. Oh, sorry. And then I can, of course, back here. So you see the distance here is, of course, longer than 8, and I am respecting the rule. Either I am going horizontally or vertically. But the point is that in the Euclidean metric, the shortest, I can talk about the shortest path, but here in Taxicab Metric, there is no the shortest path. There is a shortest path. So this is a shortest path. This is also a shortest path. Okay, why this is called Taxicab Metric? Because, for example, but sometimes, by the way, this is also called the Manhattan metric. So, for example, you can assume that you are living in a city, and then, for example, these green lines that I am drawing are the roads. And so let me just complete it a little bit. I'm trying to make all the sizes the same. So let us pretend that, yes, all the sizes are the same. So now every black square is a building, and these green lines that you see are actually roads. So now assume that you are here and you want to take a cab so that it takes you to this point here. Okay? So for example, the taxi can start moving here. Of course, you cannot go directly here. You cannot go directly here because in order to do that, you need to have an airplane so that you can fly over the buildings. But here you have a taxi. So the taxi starts from here, go horizontally, for example, faces a traffic jam here. That it can go upward and then facing a traffic jam, for example, here. And it can actually takes you and reach you here. Okay? So this is the path that you see. This is one of the shortest path if your metric is the taxicab metric. And that's why the reason it's called the taxicab metric. Okay, so the first thing, of course, my duty is to show that this is indeed a metric. So how should I do that? I need to check the properties of a metric. The first thing I need to do, I need to convince myself for any pair of points from the plane, the output is actually a non-negative real number, which is true because you see the output is the sum of two absolute values. This absolute value is always non-negative regardless of the values of x sub a and x sub b. And this is also non-negative, so the sum of these two is always a non-negative. So the first condition is really met. The second condition is that I need to convince myself that this is 0 if and only if the points are the same. Of course, from this direction to this direction is extremely simple, because if the points are the same, it means that the x-coordinate match. The same reason y-coordinates also match, so this difference is 0, this difference is 0, so this means that the total difference is also 0. So it is clear that if these 2 points are the same, the distance, the taxicab distance is also 0. And the other way around, if the taxicab distance is 0, what can I conclude? If this is equal to 0, because this is non-negative and this is non-negative, and the sum is supposed to be 0, it means that both of these two should be 0. And if they are 0, it means x of a is equal to x of b and y of a is equal to y of b. So this means that these 2 points are actually the same points. The next thing I need to check is the symmetry. Why this metric is symmetric? The reason is that, let us assume that I am asking you about the distance from b to a rather than from a to b. Then the formula that I will have, these 2 terms will be interchanged, these 2 terms will be interchanged as well, and then I have a minus sign. So the effect of this interchange is that I will have an overall minus sign, but that overall minus sign will be cancelled because of these absolute values. So at the end of the day, the distance from a to b and the distance from b to a are exactly the same. So this is indeed a symmetric function. Of course, as usual, the harder part is to convince ourselves that this satisfies the triangle inequality. So what we do, we assume that a, b, and c are arbitrary points in the plane. We need to convince ourselves that the distance, taxicab distance from a to c is less than or equal to the taxicab distance from a to b plus the taxicab distance from b to c. And if I want to translate this in the language of this formula, this means that the left hand side becomes the sum of 2 absolute values. Each one of them becomes the sum of 2 absolute values, yes? Okay, so how should I fill up them? The first one is x of a minus x of c. The second here is y of a minus y of c. And then here I have x of a minus x of b. And then I have y of a minus y of b. And here I will have x of b minus x of c. And finally y of b minus y of c. So I have to convince myself that this is indeed true. But that is very simple, not hard, but let me remind you of what we had before. This is a very famous inequality. I urge you to memorize that. So if m and n are actually real numbers, if I add them and then I want to take the absolute value, this is in general less than or equal to the absolute value of the first number plus the absolute value of the second number. So now how can I prove this using this inequality? I will start from here. I would say that x sub a minus x sub c can be written as x sub a minus x sub b plus x sub b minus x sub c, yes? So what I did, I just added x sub b and subtracted, so nothing has changed. They are cancelled and this equality is valid. But now I will give the role of m to this and I give the role of n to this, so this becomes less than or equal to the absolute value of m, which is x sub a minus x sub b plus the absolute value of x sub b minus x sub c, which is the second. And similarly, I can write that y of A minus y of C. I don't want to go through the details, but you can continue similarly and reach to this, that this is less than or equal to y of A minus y of, yes, y of A minus y of B plus y of B minus y of C. So what I have shown so far, I showed that this one is less than this sum. I showed that this one is also less than or equal to this sum. So now if I add them side by side, when I add these two, I will get exactly what you see here on the left hand side of my inequality. And when I add these, then I will get the sum here. Yes, because these two gives me, these two will give me the first pair, and these two will give me the second pair. So this means that yes, this is also indeed valid. So really we showed that this is a metric. Okay, so let us discover some geometry about this metric in this lesson. So what we do, the first thing is actually, let us go back to our friend, the circle. For example, let us consider that you have a coordinate system here. This is the x-axis and this is your y-axis. Oh, sorry. So this is the y-axis. Okay. And now my question is that, can you draw a graph that represents the circle centered at the origin and radius r? Okay. But to show that I want you to use the Taxicab metric, let me put an index t here. So I am asking you to draw the graph of the circle centered at the origin with radius 1, but according to the Taxicab metric. Okay, so let me write the definition. The definition, the abstract definition of a circle, if you remember, is the set consisting of all points where in your set. But what is your set here? Your set is r squared, with the property that the distance from that point to the center, which is in this case O, is equal to your radius, in this case 1. And if you don't mind, let me equip this one with this little this index t, so that emphasizes that this is indeed the Taxicab metric. So now if you want to understand, so this is the abstract definition, this is a set, but if you want to represent it on the coordinate system, you need to understand this a little bit better. So you are looking for the all typical points in r squared. So I would say that let A be of coordinates x and y, because still I don't know, I want to discover where these points are located. So let me call the x coordinate of those points x and the y coordinates y, and then try to understand this. Okay, according to this Taxicab metric, this can be written as the sum of two absolute values equals to 1. But how can I fill up the absolute values? The x coordinate of this point minus the x coordinate of that point. So the x coordinate of point A is x, the x coordinate point of the origin is 0. So this becomes just simply x minus 0, and then the difference between y coordinates. The y coordinate of A is y, the y coordinate of the origin is 0. And this can be simplified more to this equation. Absolute value of x plus absolute value of y equals to 1. Yes? So this is the equation that I get. If I can draw, if I can represent all the points whose coordinates x and y satisfy this relation, then the graph of this circle manifests itself on the coordinate system. Okay. Of course, you can use GeoGebra to draw that graph. I think it is capable of doing that. We can test it later. But if I want to draw it myself, you know that you need to get rid of the absolute value. But of course, to get rid of the absolute value, I need to know if x is positive or negative, the same for y. So I need to consider 4 scenarios. So I will consider the case that x is positive, y is also positive. One scenario is that x is positive but y is negative. One scenario is that x is negative, y is positive. And finally, a scenario that x is negative, y is also negative. So in that case, if both of them are positive, I don't need these absolute value signs at all. So this just becomes simply x plus y equals to 1. But this is just simply the line y equals to y minus x. So the k value is negative 1, but the y-intercept is 1. Okay, if I want to draw that, so let us assume that this point is 1 and the k value is also 1. So if I want to draw that, I need to draw it like this. So this is the line, y equals to 1 minus x. But not all points are acceptable because this relation is equivalent to this relation under these two constraints. So it means I need to consider both x and y positive. So it means that I have to be in the first quadrant. I have to be on this line on the one hand, and I have to respect this constraint to be in the first quadrant. So you see that only this part is acceptable. Yes? So this means that if I want to draw that, only this part is acceptable. But I also have to be a little bit careful about these points that I filled up. Are these also acceptable? Because I am assuming that x and y are strictly positive. But yes, these points are acceptable. Why? Because, for example, is this point acceptable? Let us check. The coordinates of that point, the x coordinate is 0, the y coordinate is 1. Do you think that these two numbers satisfy this equation? Yes, absolute value of 0 plus absolute value of 1 is indeed 1. So this is also indeed a point. Okay, so let me try to clean this. So you know that these 2 points are also included. This line segment is also included. Okay, this line segment is included because of these constraints, and then I manually check that this point is acceptable. You can also check that this point 1 and 0 also satisfies the relation. That's also acceptable. Okay, so let me make this a little bit better. So all of them are acceptable, so this is the line. So let me make it clear. Yes, hopefully this somehow works. So this point is 1 and this point is also 1. But let me do one more step. So for example, what happens in this scenario, x is positive, so I can just remove the absolute value, but because y is negative, I remove the absolute value sign, but I have to multiply it by a negative sign. So this becomes x minus y equals to 1, then this means that y is equal to x minus 1. So the k value is 1, the y-intercept is minus 1, so what happens? It becomes this. Yes, so let me change my color. So, and for the same reason, this point is also acceptable. And I really don't need to continue this line because I have to respect that x should be positive, y should be negative, so I am in the fourth quadrant. So only this part is acceptable. Okay, so that's correct. And then I don't want to continue, so this one gives rise to minus x plus y for the same reason. So this means that y is equal to x plus 1, and this means minus x minus y is equal to 1, and this implies that y is equal to minus x minus 1. And if you complete those two, you will get this picture. You will get this picture. Okay? So congratulations, this is your circle. So here your circle is actually a square. Okay, so if you are living in a universe so that the Taxicab metric is popular there, this is the shape that you call a circle. Even though in the Euclidean metric, in the universe that we are living, this is called a square, not a circle. Okay. So that was actually interesting to see. Another notion is, let us try to actually warm up a little bit with this new metric and discover a little bit interesting things. Let me talk a little bit about the perpendicular bisector. Okay, so let me review a little bit about this concept from just the normal Euclidean geometry. So for example, if you have 2 points in the plane A and B, so what you do, if I want to talk about the notion of perpendicular bisector of the line segment AB. So I have my line segment and I want to know the perpendicular bisector of that. Yes, so 1 2 3 4 5 6 7 8 9. Okay, so here is probably the midpoint. So what is the meaning of perpendicular bisector? It means that you find the midpoint exactly, so let me call it M, and you draw a line perpendicular to line segment AB passing through the midpoint. This is called the perpendicular bisector of line segment AB. So let me call it delta, this line. But you see here I defined this notion of perpendicular bisector by the notion of perpendicularity. Perpendicularity means that you have to measure the angle here, okay? But in a generic set, the notion of angle is still absent. So that is one of those things. So the notion of distance and length is not in general present in an abstract set. We realize how to give meaning to the distance for an abstract set. We need to also learn how to give the meaning to an angle for an abstract set. Okay, so that is also the notion of metric added to a set gives rise to the notion of a metric space, and then giving meaning of an angle to an abstract set gives rise to the notion of inner product space, an inner product space. But I don't want to go through it. But my goal is here is to make sense of the perpendicular bisector only formulated in the language of distance. Okay? How can I do that? So let me just formulate the question a little bit more tangible. My question is that if I give you these 2 points on the plane and I ask you, and I equip you with the Taxicab metric, and I ask you draw the perpendicular bisector of your line segment using the Taxicab metric. So you cannot say that, okay, I draw a line perpendicular to AB, since we don't know the notion of the angle yet. So how can I formulate this so that I can use only the idea of distance to formulate perpendicular bisector of AB? If you remember, in Euclidean geometry, we learned that the perpendicular bisector of a line segment is the loci of all points on the plane which are equidistant from the ends of the line segment points capital A and capital B. What do I mean by that? It means that if you pick any point on the perpendicular bisector and connect it to the end points of the line segment, this distance and that distance are the same. These lengths are the same, no matter where you choose your point. For example, if I choose this point here, of course the distances are different, but the point is that whatever this distance is, that distance is also the same. Okay? Conversely, if I give you a point whose distance from these two are the same, then this point has to lie here. It cannot be here. Okay? So not only whenever I pick a point on the perpendicular bisector, the distances from that point to the end points are the same, but also if I give you a point which you don't know is on the perpendicular bisector, but you know that the distance from that point to the end points are the same, you can immediately conclude that this point is on the perpendicular bisector. So you see that this is another way of formulating the perpendicular bisector without even invoking the notion of perpendicularity or the angle. Okay, so the perpendicular bisector is the loci of all points on the plane that are equidistant from the endpoints of the line segment AB. So this can be formulated in this new taxicab metric again. Okay, so let us be a little bit more practical here. So I go here, so let me set up a new coordinate system for you. So this is the x coordinate, and this is my y coordinate, my y-axis, sorry. Okay, so let me take this origin, and let me take this one, 1, 2, 3, 4. Okay, so let me take this one, but not 4. Let me call it point A, and let me say that this point is 2. What I want to do, first I want to draw the perpendicular bisector of this line segment using the Euclidean metric and using the Taxicab metric. For the Euclidean metric, actually, because that is the normal Euclidean geometry, we don't need to bother at all because we have the notion of perpendicularity there. So what I do, I find the midpoint and I draw the perpendicular line to that. So this is delta, the perpendicular bisector of this line segment using the Euclidean metric or Euclidean geometry. But let me try to find the perpendicular bisector of the same line segment, but this time I use the Taxicab metric. Okay. So how should I define that? So let me write delta, but equip it with t, so it means that I am using the Taxicab metric. This is the set of all points like A, where, not like A, I have already used letter A. So like M, where on the plane, so that the distance, which distance? Taxicab distance from M to O, one end of the line segment, is equal to the distance from M to A. This is the abstract definition of the perpendicular bisector. Okay, but what is this one now? Okay, I am looking for these points M. I don't know where these points are on the plane, so I would say let this point has two coordinates. Still, I don't know. I want to discover. Let M be this point with coordinates x and y. Now, if I ask you what is the taxicab distance from M to O, you will say this is the distance, this is the absolute value of the difference between x coordinates. The x coordinate of the origin is 0, of course, plus the absolute value of the difference of y coordinates. So you simplify it, it becomes just simply this. And then you calculate the distance, the taxicab distance from M, but this time to point A. So what are the coordinates of point M? A. It is 2 and they are 2 and 0. So this becomes absolute value of the difference between x coordinates, which is x minus 2, and then I have plus absolute value of y minus 2, y minus 0. And if I simplify that, it becomes absolute value of x minus 2 plus absolute value of y. But now my demand is that these two should be the same. So this means that absolute value of x plus absolute value of y is equal to absolute value of x minus 2 plus absolute value of y. But then something interesting happens, and these two absolute values are cancelled from both sides. And then what I can conclude is that the absolute value of x should be equal to absolute value of x minus 2. So this means that I am looking for these points, but I see that there is one constraint for me. I do not have any limitations on y, because you see y is cancelled. I have only limitation on my x coordinates. So I need to solve this equation. So you know that two absolute values are equal, so if and only if, because these are both directions, if and only if either these numbers are equal, or this symbol means or, they are opposite and this is equivalent to saying that this and that are cancelled, so I get 0 equals to minus 2, or I multiply this minus sign in, it becomes 2 minus x. So, but you know that this is not possible, so it is not happening, so the only thing that you have is this one. And if you solve that one, 2x is equal to 2, x is equal to 1. Okay, so what does it mean? It means that if you are looking for a point M so that it satisfies this condition, you don't have any limitations on y, but you have a limitation for your x. X should be 1. Y can be free to be anything. So this means that again you will get the same line. Okay, so what happens if I call this one a perpendicular bisector in the Euclidean geometry? We realize that these two match actually. Okay? Okay, but of course, if you remember, in this here, we calculated the distance, the Euclidean distance, you see, and the taxicab distance for the same pair of points are different. So you might think that the notion of perpendicular bisector, even though you realize these metrics are different, but you might think that, okay, they always give rise to the same perpendicular bisector for any pair. Okay, of course, this is not true. Let me try to convince you from two perspectives. I will give you another surprising example later, but let me try to understand a little bit the difference between the Euclidean metric and taxicab metric from other perspectives. The reason that here these two match, I think the reason is that because this line is a horizontal line. Okay, if you are in a single dimension, there is no way that you can detect the difference between Euclidean metric and taxicab metric. Let us try to delve a little bit into it. Okay, so for example, assume that you have access to two dimensions, but you are creating electronic gadgets for people who are living only in one dimension. So you yourself have access to the second dimension, but let us assume that there are creatures living only in one dimension. And because you have a more advanced technology, you are making gadgets for them so that they can measure the distance between the points in their universe. So for example, let us try to imagine something like this. You have an electronic gadget. Let me put E here for Euclidean, and it is equipped with two wires with two electrodes on top of that. And then what do? You take these two electrodes and put it on the point of a plane, and then this gadget is designed in a way that it gives you the Euclidean distance between 2 points. So you change the points, you get a different probability number, but that is also the Euclidean distance. And then you develop some different gadget, similar gadget with the same structure, but I write a T over it. So this means that this is a gadget that only measures the distance of 2 points in the taxicab metric. Again, so you choose 2 points and then put one electrode here, put another electrode here. This gadget reads the distance between these 2 points, but not the Euclidean distance, the taxicab distance. Okay? And then after you provide them, you send them to this world that they are only living, they have only access to one single dimension. I want to show you that these creatures cannot feel the difference between these two. So if you live in one dimension, there is no difference between Euclidean metric and the taxicab metric. It is simple. For example, so let us choose 2 points here. So let me choose a point A and a point B. So from your perspective that you have access to the second dimension, you know that, for example, the coordinate of this point might be A, but the second coordinate is 0. From their perspective, living here, they only have access to this number. They are not even aware of 0, okay? And then you have here, for example, B and 0. Okay, and then these two, the people living in this, they want to use this gadget, put one electrode here and one electrode here, and this gadget will reach the distance, the Euclidean distance between A and B. Okay, so the first gadget, the reading on the first gadget is what? Is this square root. The difference between x squared, the difference between x coordinates squared plus the difference between y coordinates squared. So this becomes simply square root of a minus b squared, but this is simply just absolute value of a minus b. So if these people use this gadget for these two typical points, they will get this one. And then if they use the other gadget, which is taxicab gadget, then what they do, they will actually calculate this, because this is designed in a way that it calculates this. But in this case, the difference between x coordinates is a minus b, the difference between y coordinates is this one, and then they will get the same answer. You see, so even though these are really different, because for example, if you take one point, put it here, and then one point, put it here, the taxicab distance between these 2 points is this sum, but the Euclidean distance between these 2 points is this line. Okay, and they are really different. But when it comes to one dimension, you cannot feel the difference. So for the people who are living in one dimension, actually the Euclidean distance and the taxicab distance are actually the same. So that's also good. So the number of dimensions of this space has somehow some effect in understanding the metric. So you have two metrics, they are indistinguishable in one dimension, but if you go one dimension higher, then you can differentiate the difference between them. So that's something. And the reason probably that you couldn't differentiate this delta with respect to the Euclidean metric and delta with respect to the taxicab metric is that because this line is embedded in one dimension. It's not extended in 2 dimensions. Of course, line is always one-dimensional, but if I draw it like this, I am embedding it on this x-axis, which is a one-dimensional line. But if I put it here, this means that I am embedding it in 2-dimensional space. Okay. So that is actually good to know. Okay, now what I can do, let me give you another example that you can see the difference, and there are some interesting things going on here. So what we do, let me still continue the notion of perpendicular bisector, but from the experience that I got here, let me change my points. And let me try to draw the y-axis here. Okay. And then let me again take one of my points, this still the origin, but let me, for example, take this point here. Let me go one more here, and then let me call it A, but let us assume that this point x coordinate is 2 and y coordinate is 2, and then this is now my blue line. What I want to do, I want to find the perpendicular bisector of this line segment oriented in this way. And this is the x-axis and that's the y-axis. Okay, so the Euclidean one is actually very simple. So what is the Euclidean one? So let me just show it to you. So you find the midpoint here, this is it, and then you draw a perpendicular bisector and then continue it from both directions, yes, until infinity. So this is the perpendicular bisector. I will do it later, okay? I will add it to my picture later. But let me try to understand what is delta equipped with taxicab metric. Of course, the definition, the abstract definition is exactly the same. So I am looking for all possible m's on the plane r squared so that the taxicab metric from m to o is equal to the taxicab distance from m to a, yes? The taxicab metric from m to taxicab distance from M to O is equal to the taxicab distance from M to A, and then I want to solve that problem. Okay, so but let me write the taxicab distance from M to O. Again, as before, I will call M to be a typical point X and Y. So this becomes the difference between X coordinates. Again, this will give me the same result. It doesn't matter. But this time, if I want to find the distance from M to A, this becomes absolute value of X minus the X coordinate of A, which is 2 in this problem, plus the absolute value of Y minus the Y coordinate of A, which is 2 again. And if I put them equal together, then what happens? Absolute value of X plus absolute value of Y becomes equal to absolute value of X minus 2 plus absolute value of Y minus 2. And then, of course, it is a little bit cumbersome task to understand how this relation manifests itself if I find all possible points with coordinates X and Y satisfying this condition. And the answer becomes a little bit surprising. Okay? But I would recommend try to see that if GeoGebra is capable of doing it. Okay? Okay, so now I'm going to GeoGebra. I want to see how GeoGebra answers this. And then, of course, now that we are going to GeoGebra, if you don't mind, let me also check this one. So I will give GeoGebra to draw this relation to see if we can confirm what we have done is right. Here, I will not actually do it manually here for you, but I will give you the final answer, and I want you to be able to do it yourself. That is a good exercise for you. Okay, but let us go and try to test GeoGebra. Okay, now we are in GeoGebra. First, let me check that equation that we have. So I choose absolute value of X and then plus absolute value of Y equals to 1. And that's exactly the square that I drew it for you. So yes, it is working in that case. But now let me make it a little bit more complicated. The equation I got for the perpendicular bisector of the line segment OA using Taxicab Metric. So the equation was this: absolute value of X plus absolute value of Y equals to absolute value of X minus 2 plus absolute value of Y minus 2. Okay, and then a very strange graph appears. I can understand the problem of GeoGebra in visualizing this. So just have this in mind, because the real answer is actually this part of this. So if I want to show it for you, the real graph will be something like this. So if I draw this line segment, say for example here, yeah, up, for example, up to here, and then here up to infinity, minus infinity. So you see that this perpendicular bisector covers every point on this half plane. This is why GeoGebra is acting a little bit weird here. Also, it covers all the half plane here. Okay, and then also contains this line segment, which coincides with the Euclidean perpendicular bisector, but it also contains these lines. So this is why GeoGebra is acting a little bit weird. But it was good to see that how it works. So let me just go back to the lesson. Okay, so what we learned there is that if you want to draw this, so if you remember, let me now add the Euclidean one. So the Euclidean one was this line. So if I can draw it, okay, but for the Euclidean one it continues forever from both sides like this. But now I will pick up a different color, so I will draw it here. So that is of course a part that we have. Still we have this one, but then you need to be able to convince yourself that this semi-line, this semi-line, this semi-line, and that semi-line, and including every point here that you see, similarly every point here that you see, yes? So these pinkish parts all is, let me call them all the pinkish part. This is delta taxicab, but this one is delta Euclidean. Okay, so this shows that there is a very actually big difference between these two metrics. Okay, but from mathematical point of view, this metric, Taxicab metric and the Euclidean metric are just two metrics. And all of them are consistent with the concepts that we have learned so far. So none of them has any advantage over the other one from mathematical perspective. But of course, a physicist is also concerning about which one, if any one of them, somehow describes our universe more accurately. This is not something that mathematics by itself can answer. Okay, we need another mechanism, which is the experiment. We need to do some experiments to realize which one of these metrics, even though both of them are mathematically sound and plausible, but which one describes the universe? Which one I am supposed to use to measure the distances between the points? So let me try to somehow, with a simple experiment type thinking, to convince you that no, the taxicab metric is not a good metric for our universe, at least what we see around us. Okay, for example, let us assume that I have a coordinate system and I have a rod of length 1 meter, for example. I put it from here to here, so let us assume that this length is 1 meter. Okay, so this point from O and to A. So let us assume that this is a rod of length 1 meter. So, and you see that when I put it here, we learned that the taxicab distance between O and A and the Euclidean distance between O and A both are the same, and that's 1. So in our universe, we used to this way of thinking that if I rotate the rod, I will not affect the length. Yes? So, for example, if I start rotating my rod 45 degrees so that I reach here, still I have 1 length unit. Yes? So it's not a good picture here. I need to make it a little bit shorter. So because if I just do it like this. Okay. Now let us say that this angle is 45 degrees. Now I reach to point B. If I ask you what is the Euclidean distance between these 2 points, not surprisingly you answer 1 length unit, because you know that in our universe the orientation of the rod will not affect its actually length. And the calculation confirms that. How? If this is 45 degrees and this is 1, I can find the coordinates of B. Very simple, yes? I draw a perpendicular line here, and then I say that this is the 1 times cosine 45, which becomes 1 over square root of 2, and this one is also the same, because if this is 45, that's also 45. So the coordinates of B are 1 over square root of 2, 1 over square root of 2. So now if I measure the distance from O to B by Euclidean metric, what should I do? This is just the normal distance. I have the square, the difference between x coordinates, 1 over square root of 2 minus 0 squared, 1 over square root of 2 minus 0 squared. The difference between x squared, y squared, yes? What happens? It becomes square root of 1 over 2 plus 1 over 2, which is square root of 1, not surprisingly at all. It is 1. That is exactly according to our intuition from what we realize from the universe around us. But now if I calculate the taxicab distance from OB, then it becomes the two absolute values, the difference between x coordinates plus the difference between y coordinates. This time it becomes 1 over square root of 2 plus 1 over square root of 2, which is 2 over square root of 2, it becomes square root of 2. And this means that the length is no longer. Okay, so you see that this is now according to our intuition. Of course, this analogy is not 100% correct, because setting up a coordinate system has also something to do with the notion of the length. Now I'm assuming that the points and the coordinates are the same in two geometries, and I am comparing only the distances between 2 points. Okay, but I just want you to understand this point, that understanding which metric is suitable for our universe is not the job for mathematics. You need to do it in physics by doing an experiment. Let us say what I said here is correct, then it means that the taxicab metric is not a good description of our universe, because the implication of accepting this metric for our universe is to accept that by rotating, by changing my orientation of the rod, changing the orientation of my rod in a space, I am affecting its length, which is not what we see around us. So then we see that, okay, even though these two metrics are mathematically sound and consistent, we need to prefer the Euclidean metric over the taxicab metric. Okay, so that is also an important point that I want you to know about. But now let me also try to describe a little bit about the mindset of mathematicians. Okay, mathematicians usually have this tendency to generalize the concepts, okay, and delve more into the imagination. Okay, for example, let us try to compare the Euclidean metric and the taxicab metric from another perspective. So the taxicab metric between points A and B is like this: the absolute value of the difference between x coordinates plus the absolute value of the y coordinates, yes? And then of course the Euclidean metric for the same pair will give you this result, square root of absolute value. By the way, there is no difference here between absolute value and the pair of brackets, because this power is even, yes? So, in mathematics, we are very interested in finding the differences and commonalities, the similarities, yes? So we learned that these two metrics are really different, acting really different, but is there any way that we can find some commonalities between them? For example, this is the mindset of a mathematician. Mathematician probably asks himself that, is it possible that I can find a formula with some parameter in it, so that by changing the parameter into one value, I generate the taxicab metric, and if I change that to another value, I generate the Euclidean metric? And I hope you see that this is not hard to answer to this question positively. For example, we can say these two metrics are actually particular cases of another formula. So let me call it D of A and B. Then instead of writing it like this, I would write it the pth root of absolute value of xa minus x sub b to power p plus the absolute value of ya minus yb to the power of p. Okay, and then because I want to show the dependence of D to this parameter P that I introduced, so let me equip it with an index P here. I don't think it is that hard. If you know what you are doing, that is not hard to find a formula that generates these things. Why? For example, if I choose P equals to 1, then D1 of A and B reads like this. This becomes the first root of absolute value of xa minus xb to power 1 plus absolute value of ya minus yb to power 1. But the first root means the number itself, so this becomes simply x of a minus x of b absolute value plus y of a minus y of b absolute value. But if I ask you what this is exactly the taxicab metric. And if I choose p equals to 2, then d2 sub 2 of a and b, this becomes the second root, but for the second root you know that you don't write this number here. So that is just the second root of absolute value of x of a minus x of b to power 2 plus y of a minus y of b to power 2. What is this one? Nothing except the Euclidean metric. Okay? So we were able to write at least a formula, that this formula generates the taxicab metric if I choose p equals to 1, and it generates the Euclidean metric if I choose p equals to 2, even though taxicab metric and Euclidean metric are really quite different. But I was able at least to unify them under one type of formula. Okay, and if you do that, mathematicians cannot resist about this question, asking this question: what happens if p is 3? What happens? Why should I stop here? P is 1, here p is 2, but why should I stop with 2? Let us go further. So what happens if p is 3? What happens if p is 4? So for example, let me write 3. Let me choose p3, and then I will have this. Okay? Then, of course, there is an important task they have to do. Okay. So they generate this new formula, but there is one question to answer. Is it guaranteed that d sub 3 that I generate by just pure imagination is also a metric? You see, the answer to this question is probably not that easy. Of course, the first few axioms are simple. Is the output non-negative? Yes. This is non-negative, this is non-negative. And then if you put this one equal to 0, it is not hard to convince yourself that A is equal to B and the other way around. Symmetry is extremely simple. But the point is that, is it correct that this function also satisfies the triangle inequality? If the answer is yes, then yes, this is guaranteed to be a metric again, so I can add my metric to this class of metrics. But then the question is that, if I go to 4, is it still a metric? And can I find a way to generally prove it for any p? I am just trying to think loudly if you are a mathematician. This is the way that mathematicians think. Okay? One of the ways. So they have the tendency to generalize things. And then, by the way, it was not hard. If you ask this question from yourself, is there any way that I can unify these two formulas under one formula? And if you are able to do that for p equals to 1, p equals to 2, everyone asks the next step. What happens if p is 3? I think it's very natural. Okay? Even though physicists might not be interested in these metrics because they realize by some experiment that the metric describing our universe is only the one, or at least we see it in classical mechanics, that p is equal to 2. Okay? And then, of course, you see that, you remember, we wanted to prove that this Euclidean metric is indeed satisfying, does satisfy the triangle inequality. It was so lengthy, but now let us assume that I want to work with the third root, with the fourth root. It becomes very, very hard if I want to accomplish. And if I don't do that, still I cannot rely that I have a metric. So sometimes the task, so even if you succeed to show this is a metric, you haven't added something to the concept of the metric space unless you have discovered a whole class of metrics there. And these metrics, by the way, are extremely important. These are the foundation of the very important spaces called L to the power of p spaces, which are extremely important, for example, if you want to study quantum mechanics from mathematical point of view. Okay, again, let me describe you another tendency. So if you remember, all these metrics that I described for you are a little bit artificial. Why is that? Because they are working in a plane, but at least we can see around us that we are living in a space with 3 spatial dimensions. Okay, so now here, why I need to have 2 coordinates only? Because in reality, I have at least 3 coordinates. And if I add time to it, I will have 4 coordinates, yes? In the string theory, we can have 10 coordinates, spatial coordinates, and 1 temporal coordinate, okay? So the next thing is that, and if mathematicians realizes that there are higher dimensions somehow involved, they don't go to 2, 3, or 10, or 11, they suddenly go to the most general case, and they say that, okay, let us take the n dimensional space. For example, they would say that, okay, let me my point A in n dimensional space has n coordinates that I write them with x1 up to xn, and point B has so let me denote it by another letter, y1, y2 up to yn, and then I want to find the distance between them with for every p, possible p, positive p of course here. Then they ask themselves, is it true that this is also a metric? So I think this is a good place for mathematicians to stop. Of course, they also think about what happens if p goes to infinity. Yes. So they are really imaginative, and it is really, I think, extremely good and fun. Okay. And usually in the future, somehow some smart person will find some application for these imaginations at some point. The history of science, especially physics, has revealed this over and over during the time. Okay, so the next lesson I will try to delve a little bit here, because, by the way, to show that these are metrics are very technical. The only problem that we are facing is the triangle inequality. And then to be able to prove the triangle inequality there, I need to talk a little bit about 3 different inequalities, and they are carrying the names of mathematicians. So Young inequality, Hölder inequality, and finally Minkowski inequality. So finally this Minkowski inequality, so these 2 inequalities prepare the setup, prepare everything for us, and finally Minkowski inequality proves that this function in n-dimensional space for p greater than 1, of course equal to 1 is also true, p greater than or equal to 1, always satisfies the triangle inequality. Surprisingly, even though these are extremely technical problems, but it is exactly at the level of the knowledge of a high school student, even though of course this is a very hard problem, but I think it would be good if I start proving this in the next session, at least for 2 dimensions. Okay, so that would be instructive to see how creative mathematicians could be in their work if they want to do something. Okay, and then you see that sometimes these, so you hopefully so far you realize that some part of mathematics is abstract thinking and then understanding the concepts, but some very important part of it is also technicalities. So you should be able to overcome with the solutions and proofs of specific individual problems if you want to go forward. Okay, so I hope that this video was useful for you. Until the next video, be safe and goodbye. Thank you.